Good afternoon, all. My name is Santoshi Rani from VLSI department. So today's section is on FPGA based systems. First of all, we would like to thank you with the Kuppam Engineering College Department of ECE to conduct this FPGA based systems. The convener of this webinar is Dr. G.N. Kodanda Ramaiah sir and the coordinators Dr. P. Ajay Kumar Reddy sir and Dr. K. Rasa Rasadurai sir. Thank you for conducting this webinar. So before moving to the FPGA based systems, first we have to know about the VLSI, right? So what is VLSI? VLSI stands for the Very Large Scale Integration Circuit. It is a technology, the type of the semiconductor technology that involves packaging thousands and the millions and the even millions of the electronic components such as the transistors, diodes, resistors and the capacitor on a single chip of a silicon. Like we are going to integrate these components like transistors, diodes, resistors and the capacitors on a single chip. So before this, like here we have the scale integration, right? Large scale integration, like very large scale integration. So before this, we have the different types of the scale integration circuits here. So before moving on to this, we will know about the history of it. So, so first we have the small scale integration. That is nothing but the SSI. And it was introduced in the 1964. The number of transistors used in the small scale integration circuits are the 1 to 10 transistors were used. The number of the logic gates are the 1 to 12 logic gates were used in the small scale integration. So, in the medium scale integration circuit, it was introduced in the 1968. The number of transistors are used in the medium scale integration are the 10 to 500, and the number of logic gates which we have used in the medium scale integration circuit is the 13 to 99. Whereas in the large scale integration circuit, it was introduced in the 1971. The number of transistors are the 500 to 20,000. So the number of logic gates are the 100 to 9,999. So in the very large scale integration circuit, here it was introduced in the 1980. The number of transistors are the 20,000 to 1 lakh. So in the logic gates are the 10,000 to double nine and triple nine. In the ultra large scale integration, it was introduced in the 1984. It was like when compared to the VLSI, in the ultra large scale, the more number of transistors were used, but present we are using the very large scale integration circuit here. So what is the difference between this small scale integration circuit, medium scale integration circuit and the large scale integration circuit and the very large scale integration circuit means the number of transistors. Here you can observe the, here we have used the only the 1 to 10 and in the 10 to 500, right? So whereas in the VLSI we have used the 20,000 to above, like above 20,000 we have used the transistors to design a circuit, like how you're going to integrate that one by using the transistors, right? So you need the huge number of transistors. So for that we are going for the very large scale integration circuit there. So let's, we will move to the applications. So in the autonomous vehicle, so VLSI technology is a crucial role for the real-time processing. Like in the self-driving cars, it is used in the sensors, the radar systems, and the onboard computers that process the data and then making the driving decisions. Like in the autonomous vehicle, we can use this. Like self-driving cars, also we can use this one. And in the IoT, VLSI chips are used in the IoT devices for the data processing and in the sensor interfaces and the connectivity in the enable real-time data collection and the analysis in the various application like for the smart homes to industrial IoT. We can use this one. Like in the smart home application also we can use this VLSI application as well. And in the healthcare or in the healthcare also we can use this VLSI application as well. In the robotics, like in the robotics also we can use this VLSI applications. So whereas in the to design the pacemakers, we are going to use this one like VLSI. This is also one of the example here. And in the real time, like in the image and the video processing also, we are using the VLSI application here. So in the computers also, VLSI technology, it is used to develop the for the microprocessor and other computer component like for the memory and the storage devices. We are going to use this application. And in the communication, like such as in the mobile phones routers, we are going to use this VLSI application as well. In the automotive, in the control electronic control units and in the automobiles or the transmission or the in the control to control the various systems such as the engine or the transmission or the brakes, we are going to use this automotive. For this application we are going to use this VLSA there. In the medical, right, in the healthcare is nothing but the for the heart monitors or the pacemakers, we are going to use this one. In the aerospace and in the defense also, we are going to use this VLSA application there. So our topic is on FPGA, right? So what is FPGA? So FPGA stands for the Field Programmable Gate Array. It is an integrated circuit. That is nothing but the IC. IC is nothing but the, we can say it is a chip or the microchip which we can see in our mobiles, the laptops. So it consists of the internal hardware blocks with user programmable interconnects to customize operation for a specific application. The interconnections can be readily be reprogrammed, allow an FPGA to accommodate changes to its design or the even support a new application during the lifetime of the part. So by using this hardware, we are going to dump the code we are going to check in the today webinar. We are going to the one sample code and we are going to dump in the FPGA as well. So before going to the hardware part, first we have to know the FPGA architecture, right? So this is the FPGA architecture. So this is how the FPGA architecture looks like. In this we will be having the configurable logic blocks. So the boxes which we are seeing, this square ones, is nothing but the configurable blocks. And here you will be having the horizontal channel and you have the vertical channel. The vertical lines we can see, right? These are nothing but the vertical channel, we can say. And the boxes which we are seeing here, so that is nothing but the configurable logic blocks. And here we have the input and output pads or the input or the output blocks also, we can say. And to communicate from the configurable logic gates to this vertical horizontal or to communicate with the one component to the other, we are going to use this connection boxes here. So what is this configurable logic blocks means? Here it consists of the lookup tables, multiplexers and the flip-flops and the other elements like the specific for the specific logic functions also we can use here. Like what is the meaning of the lookup table means? It allows the a particular design to implement custom digital logic. So in this we will be having in the configurable, we will be having the lookup table and the multiplexer is there, right? We will be having the multiple inputs in the single output. For that purpose also we can use this one, and the flip-flops for the storing of the data we are using the flip-flops here. And we can take the other like for the specific logic function also we can do in this configurable logic block here. Okay, like to transmit the like for the transmission we are going to use this horizontal and the vertical channels, but the interconnection interconnections, it would provide the path for the signals to travel between the different logic elements within the FPGA to transmit the to travel the different signals, it going to show the path from the one logical element within the FPGA. Like this is the FPGA, right? FPGA type with to pass the from one path to the other path for signal. So we are going to use this vertical and the horizontal channel or the interconnections we can say. So input and output blocks or the input and output pads also we can say. It's going to perform the bridge between the external world and the FPGA. So what is the meaning of this external world, right? So in the FPGA we will be having, like, this is the architecture, right? So we will be having the input ports and output ports, right? So from the externally we are going to connect, if you want to put any if you want to connect any sensor, those all things, it can be done in this part here. The that outermost part you can see here, this is nothing but the input and the output pads. So we are going to connect the our sensors to this input and the output ports here. So this is the in FPGA we will be having the different types of families, right? We have the Spartan 3 and 3 and the Spartan 3A, different types of FPGA families we are having. The FPGA this is the Spartan 6 FPGA family. So this is how the FPGA board looks like. So here we have the we'll start from here. So here we have the JTAG header we have, and we have here VGA connector, and this is nothing but the Xilinx Spartan 6 FPGA. Okay, and this is the audio jack, and this is the micro SD card slot. Okay, these are the push buttons. Here we have the 6 push buttons we have here, and the 8 LEDs also we have here, and the dip switches, for the here we have the 8 switches here, and here we, if you observe here in the P6, P7 and the P8 and the P9, these are the nothing but the from here only we are going to give the input, the like externally from the for the sensors or the ground or the for the 3 volts we are going to give the supply here, like GPIO pins we can see here we have. First there First, you will be having the 8 GPIO pins here, like 1, 2, 3, 4, 5, 6, 7, 8. Like this it will be. And you have the two grounds, and uh, for the voltage supply, we are going to give the 3.3 volts from here. For the each and every block here, we will be having the same thing. Like 8 GPIO pins will be there, to ground, and the two 3.3 volts will be there here. Okay, so here we have the power select header will be there. Here you can see for the 1 and 2 you can use the USB power, whereas 2 and 3 for the external power supply also you can use here. Okay, so here we have the USB interface, this USB interface. From here you have to connect the USB cable to your CPU or your laptop, you can connect as well. This is the 7 segment display we can say. So this is how the Spartan 6 FPGA board looks like. Okay. So we have the FPGA, like a Spartan 6 FPGA board is there, right? So how you are going to do any project, or if you want to blink the LED or like for the home automation will be there, right? So by using this temperature sensor or the heartbeat sensor, how you are going to do this project? Like the LED should be on like for the 1 minute 2 seconds, or if the in the healthcare, if we take the BP or the blood pressure or the heartbeat rises, the LED should blink if the above certain we used to give the time limit, right? So what are the process, like when it should be on and when it should be off? Those all things will be done in the, like we are going to write the code for it, right? So how you're going to write the code? That is nothing but the HDL. What is the meaning of the HDL here? So HDL is nothing but the hardware description language. So in the VLSI, we will be having the two languages, VHDL and the Verilog HDL. So VHDL stands for the Very High Speed Integrated Circuit Hardware Description Language, and the other is the Verilog Hardware Description Language. These are the two language. In this two language, we are going to write the code and we are going to dump this code on the FPGA. Okay, so in the we will be having the system Verilog as well. System Verilog is nothing but the advance of the Verilog here. Okay, so what is the difference between this Verilog and the VSDL means? VSDL is nothing but is the older language, whereas Verilog is the like present. Mostly we are using the Verilog itself. In the Verilog only, we are going to write the code today. So the softwares which we are using to dump the code, like you have the language, that is nothing but the very long language you have, and you have the FPGA board as well. So you need the platform, right, where you're going to write that one. You need the certain software there. So the software which we are using here is the we can use so many softwares we have. Xilinx Vivado, the Xilinx ISC also we have, and the model sim also we have. So present we are using the like in this today's webinar we are using the Xilinx ISC here. So we will move to the Xilinx ISC. So I'm just constructing one example here, like how to write the code and how you're going to dump and how it will be. So further, I have just constructed the full adder here. So as we all know, like full adder, it will be having the three inputs and the two outputs. The inputs are the A, B, and the CN, and the sum and the C are the outputs here. So by using the two half adders also we can design the full adder. So here I have constructed with the, I have designed by using the XOR and the three AND gates and the one OR gate here. So let's move to the Xilinx ISC. So this is how the Xilinx ISC page looks like. Okay, so here you will be having the files, and in the files you have the new project and open project and the open example and the project browse here. And in the edit also you will be having the difference like undo and the redo, cut and the copy and the delete will be options you have here. And in the view you have the panels like toolbars and the zoom and the refresh. You have this all in the view, and the project also you have the new source, add source, those all things will be there. And this is the sources and the process and the tools which we are using and the windows and the for the layout and the help we will be having. Okay, so now I'm going to show how to create, like how to create a new project here. So just go to the files, click on the new project. So you are going to get this pop up. So here you have to give the C. We are going to write the code on for the full adder, right? I have just mentioned full adder. So I have created one folder here. So I have given the location as well. And here you will be having in the top level source type. You have to select here the HDL. HDL is nothing but the hardware description language, right? And here we have the schematic, those all things will be having EDIF or the NGC or the NGO. So we are writing the code in the hardware description language, right? So I have selected the HDL here and just click on the next. See, in the project setting we got here pop up, right? So here If you click on here in the family, like in the FPGA, we will be having the different types of families, right? So here you can see Spartan 3 at DSP or the Spartan 3 at the Spartan 3 at the Spartan 3 and Spartan 3, Spartan 6 at the Spartan 6 low power, vertex 4, 5, 6, vertex 6 low power, vertex 7, ZY and Q. These are the Spartan FPGA boards we have. So here I have mentioned, right, one FPGA board which we are using. Spartan 6 FPGA board. So here you will be having like a, so if you zoom in, here you can see it is a Spartan 6 and it going to show the device name, those all things. So the family is Spartan 6 and the device name is also will be there. See, I have given the device name as well and the package also. It's going to show the package name as well here. In the package name also it's going to show and the speed also. So by saying this, like you're going to dump this code on the FPGA, right? For that you need the which family it consists of, which device it consists of, and which package it have, and the speed as well. So these all things you will be having on your FPGA board itself. Here it will be. So here it will be. You can just what the family it is, but the Spartan 6 or the Spartan 3 or the Spartan 3A, you have to make assured about it and you have to give the device name as well. I have given the device name and the package name will be there and the speed also we have to mention here. So here downside you can see right in the preferred language. So I have told right we will be having the VHDL and the Verilog. So present we are writing the code in the Verilog. So just click on the Verilog here. Just click on the next. See here you will be having the project name which I have given the full added webinar, right? And this is my location. In this location only my file is going to store, and the devices like the family name which I have given the Spartan 6 and the package name which I have given and the device name as well and the speed it's going to show here. And the preferred language I have preferred the Verilog, right? It will show here. Okay, so just click on the finish here. So you have created the folder, right, and a certain location. So we have to write the program. For that you have to click on the, just right click on here and just click on the new source. Here you will be having the different like IP will be there and the schematic and the system generator project or the user document or the Verilog module or the Verilog test picture or the VHDL module, VHDL library and the VHDL package and the VHDL test bench and the embedded processor, right? So if you read the program in the VHDL, we have to select this VHDL module library package in the test bench. But we are writing the program in the Verilog, right? So we have to select the Verilog module here. Down and also we have the Verilog test picture. So after writing the code, we are going to like in the VLSI we have to write the two codes. Actually, the main code will be there, and the test bench TB file will be there. There's nothing but the test bench. We like what are the circuit you have wrote, right? So it's going to perform the like certain like a half adder or the AND gate or the full adder. Like how do we know like it's going to perform that specific operation like a half adder or the full adder? So we have to give the inputs, right? How we are going to give the inputs by writing the test bench here. So for the test bench, we have to select the Verilog text picture here. So I have first we have to write the code, right? So I have select the Verilog module here and I have to give the module name here. Okay, so I have the full adder here and click on the next and the next, the finish. So this is a page where we have to write the our Verilog code. Okay, so in the Verilog you have to start with the, how you're going to start the program in the Verilog by writing the Verilog like module, and how you're going to end this one by end module here. So between this, first you have to write your this is the module, right? And this is your module name here. So after that you have to open the brackets, and here you have to mention the what are the inputs and the what are the outputs you are taking. And next is the your body part, like what operation you are going to perform there. Then you have to type there, like here you have to mention the your inputs and the outputs you have to mention here in this block. So in this block, like from here to here, this is nothing but your body part, like which operation you are going to perform. So after that we are going to just ending with the end module here. Okay, so in the full adder we will be having the three inputs, right? So I have just mentioned here A, B, and the C in here. And the what are the outputs we have? We have the sum and the C out. So here we have to specify what are the inputs and what are the outputs we are considering here. So input A comma B and C. The inputs will be there for the full adder, and output like sum and the C out. So this is our output here. See here. So three inputs I have given and two outputs I have given, right? Sum and the C out. These are the outputs, and the A, B, and the C in user input, right? So we have mentioned this ABC, the input, and the sum and the C out are the output, right? Between this, like from here only, like you are going to get the three inputs, and the for this AND gate we are going to get the AB and the AC in for this AND gate, and the other AND gate we are going to give the like B and the C in, right? So uh, from this AND gate you are going to get the output, right? This output, like from this three AND gates output, you are going to give this inputs to the this OR gate here. So this connection is nothing but the wire, the internal connection. Like we can say it as an internal connection between the input and the output. If you have this connection, like this connection you have, like that is nothing but the interconnections, right? For these interconnections, you are going to mention like how you're going to write this one. So by using the wires, we are going to write the interconnections there. Okay. So I'm just considering the wires as this one as in T1, T2, and the T3 here. Okay. So interconnections we are going to represent with the wire, that I'm just giving the labeling as a T1, T2, and the T3. Okay. So for the XOR we have the sum is an output and A, B, C is your input, right? So those I'm just mentioning here. So in the Verilog, we can write the code in the three ways, like the gate level and the data flow and the behavior we can write. How you're going to write the gate level means, if you have the structure, like if you have the circuit, like how we have here, like you have on the circuit, right? By using this circuit also you can write code in the Verilog. So if you don't have the circuit, you have the equation, right? So in those cases we can write code in the data flow modeling. So if like you don't have the circuit as well as you don't have the equation as well, so you have all the truth table, right? The test conditions will be there. So you have only the YouTube, Bluetooth. So you have only the truthable will be there. So in the condition, you have to write code in the behavioral model. So I'm just writing the code in the gate level modeling. So XOR sum is your output, and a comma b. Three inputs will be there, right? A, B, and the C in. And the next one is the, here we have used the three AND gates, right? P1 I'm just considering as the one output. There is nothing but the word A comma B. The next one is a AND T2 B comma C. And the next one AND of T3 C comma A. Or finally we will be having the OR gate, right? Or COT is your output, and from the AND gates output, like from here we got the T1 as an output. From this AND gate we are just considering the T2 as an output. From this AND gate we are just considering the T3 as an output, right? This three output we have given to OR gate here. Okay. So I'm just mentioning the T1, T2 and the T3 here. So first we have mentioned here module and the module name. What are the inputs and the outputs we have? I have just mentioned here. So I have just divided what are the inputs and what are the outputs I have considered. I have this given label here. And wire is nothing but the interconnections, right? Here, like from this AND gate, we are going to get the output. That output you are going to give to the this OR gate input in the same way. So here I am just considering the three wires, nothing but the interconnections. Okay, so here we have how you have designed the full adder. We can design the full adder by using the two half adders as well. So I'm just I have just took this one. So here we have the one XOR. So for that it will be the sum and the ABC is your input, and one AND gate, three AND gates we have used here. These three AND gates outputs I have given to the inputs for the this OR gate here, and we have end this one by writing the end module here. So after writing this code, just we have to save this one. Just click on this is the file which you have created, right? Just click on it. So in this page, this is a here you are going to write the code, right? So in the left side you will be having the two blocks here. So one is the hierarchy and nothing, and the other is the processor. So what are the codes? Like if you want to write the code for the folder, you have the created one folder, right? So if I write code like for the full adder, if I want to write the by using the two half adders, so by using the two half adders also we can design the full adder circuit, right? So for this I needed two files, right? So every file, like if you're going for the any complex program also, you need the multiple files, right? Those all files will be saved here in the hierarchy. Okay, in the hierarchy only the all files will be there. So in the processor, if you want to do in the synthesize or the implementation, or if you want to generate the program file also in the configurable, like these all things will be there in the processor here. Okay, so here we have the road code here, and here you have to click on the save and just select this one, and we are going to synthesize this one. Just in the left side you will be having the display symbol, right? Just click on it. So if you want to directly dump it, like you can dump, or else if you want to check your program whether it is right, or if you have any errors on it, just click on this plus symbol. Here you will be having the check syntax, right? Just double click on it. See, it have shown the green tick mark, right? That means it has successfully synthesized. So we don't have any errors as well. So let's check with the, I'm just removing this comma. Just save the file. Just click this one and again synthesize this one. See here, you got the error, right? That is nothing but the syntax here. So this is how the, if you don't have any errors, it's going to show the green tick mark here. And if you have any errors, it will show like this. And here you are going to get the errors, like in which line you got the error, okay? See, we have done with the check syntax here. And just we are moving to the view RDR schematic here. So for the after this we are going to get this pop-up. Just click on the start with the schematic of the top level block. Just select this one and click on the OK. So see here you are going to get this block, like you will be having the three inputs and the two outputs you will be having. If you click on this block, you are going to get the, like the circuit you are going to get here. Okay. So you have design here. So you have designed the this circuit, right? So how do you know that it's going to perform the full ladder, right? So for this we have to write a test bench, right? So if you want to dump this code, if you want to dump this code on your Spartan 6 FPGA board, so how you going to do this one? First you have to click on this synthesize here. Okay, it going to synthesize your this program and you have to click on the implement design. Okay, so you have to click on the implement design here and you have to click on the generate programming file. In these only we are going to get the generate programming file here. So how you going to generate this programming file means, see in this image you can see here. So synthesize was done. It have shown the green tick mark here, and the implementation also it have shown the translate map and the place on the road also to be done. Generate programming file is there, right? To dump the code in a two ways you can dump the code in the FPGA. That is nothing but by using the like USB cable also you can dump the code, or else in the JTAG by using the JTAG. Here we have the connection, right? See in this image, by using the like this USB interface is there, right? From this also you can dump the code, or else we can take this JTAG here. JTAG header is there, right? Here from here also you can dump the code. Like how you're going to dump the code? We have two different ways, right? JTAG and the USB. So for that you have to create the bit file or the bin file. These are the files you have to generate, like to dump the code in the, like by using the JTAG or the USB you have to generate. Like in this we are going to generate the bit file and the bin file here. So if you have created the bit file and the bin file, then you have to click on the configure target device. Okay, if you click on the configure target device, it will open as this window. ISC impact window will be open. So in the left side you will be having the boundary scan, right? So you have to just double click on it, the boundary scan, then you are going to get this one. The Xilinx will be there, the Xilinx chip will be there here. So you are going to get this Xilinx image here. So you have to just click on the right click and just program it. In this way, you can dump your code from the, in this way you can dump the code by using the Xilinx ISC here. So if you have successfully done the code, it will show as the program succeeded, or else in the error block. Here you can see the error is there, right? If you click on it, it will show error. How we have saw in the Xilinx like how we got the error here before, like when I have removed this semicolon here, you got the error, right? In the same way it will show as a error there. So this is how we are going to dump the code in the FPGA. So after that, like here I have to give full adder, right? I have given the, so full first for the full adder I'm just considering three inputs, right? How I'm going to consider these three inputs, like how I'm going to mention means, like how I'm going to on or the like that. Here we have the push buttons also there, right? I'm just considering as this push button as my input, or else we can take this the switches also. So three inputs like one, two, three, and the switch one, switch two, or the switch three also I can consider like push buttons. Buttons also I can take as an my input. So three inputs I'm just considering, like how I'm going to show the outputs, like the sum and the cout, right? So I'm just considering my output as an LED here. Okay, here we have the 8 LEDs, right? By using these LEDs, I'm just going to show my output here. Like I'm just considering the LED 1 and the LED 2 are my sum and the cout. So for that, like if I'm going to, if three inputs are off, like A, B, C is off, what output you are going to get in the sum and what output you are going to get in the C out, it will show like the LED is going to blink. If it is going to blink, whereas in the sum or the C out, it will show here. Okay. So I'm just writing the test bench for my full adder, like it will perform the full adder or not. Just for that we have to click on the simulation, and here you have to like create the file, like click on the new source. Like for the main program you have for the program you have to the Relog model, right? If you want to write the test means you have to select the Verilog text picture here. Okay, just click on it and just even the label as a TV is nothing but the test bench. Click on the next and the finish. See here we have created the TB file. If you click on this plus symbol, for what you are writing the program, like for which file you are going to do the test bench means for the full adder, right? So that's the reason it have shown the UUT, like unit under test. Okay, now for the full adder here it have shown here that file. Okay, and in the Verilog we have as I've said we have to start with the module, and this is the module name, and these are the inputs. In the test bench, what are the inputs you have considered in the main file? This is the main file, right? What the main file you have took the inputs here. It going to be the register. REG is nothing but a register. It going to convert into the register here. The outputs will become the wires. So full adder UAT, like we are going to write the test bench for the, it's going to go for the unit under test. That is nothing but a UUT. You are writing the code for the unit under test bench, like test bench for the full adder. Okay, so what are the, like we are just initiating, like what are the inputs we have took in this file. I'm just giving the, I'm just doing the writing the test bench for that inputs itself. So that's the reason I have mentioned the, I'm just initiating, like dot a of a is nothing but the initiating the inputs and the outputs here. And here I'm just writing my conditions, like what are the inputs I'm just giving, like I have the three inputs, right? A will be the off, and the B will be the off, and the C will be the off. I'm just considering the 100 nanoseconds. Okay, and the next condition I'm just considering it as A equal to off, B equal to on, C in equal to off. I'm just considering the few conditions actually. I'm just changing the values here. I have given the in the three conditions, in the A B C it will be the off, and in A will be the off, B it will be the on, and the C it going to be the off. So in the A it will be the off, and the B C it will going to the on, and the A and the B it going to be the on, and C in it going to be the off. Okay, so I'm just here I have mentioned, right. I'm just considering my input are there. This push buttons or the this switches I'm just considering. If I am off, in the sense I have to click on the off one, and in the on I have to click on I have to just switch to the on button. Okay. So after writing the code, we have to save this one and just click on this test bench, and in the processor we will be having the IOSM simulator. Just click on this plus symbol, just behavior check syntax. So we don't have any errors in the test bench. So for the main file also we have to do the check syntax, whereas for the test bench also we have to do the check syntax. Okay, and we have to click on the simulate behavior. This is how the waveform window looks like. Just keep the color here, and just here you will be having the zoom to full view. Just click on it here. So here you can observe here in the count you got the this red line, right. See here the inputs. Here I have took the A, B and the C, right? Seen. So we have done only the check syntax for our program. But when we saw here, we got the one red line. That is nothing but it is the like a high, like you got the one error. So until and unless, like first you won't get the any error in the starting, but it going to check only the syntax, right? In the waveform window only you come to know what mistake, like what the where you got the error in the your program, like it going to perform the full adder or not. Okay, so if you observe here, see here, I have given the scene, right, but I have mentioned it as C. So that's the reason we did not got the output there. I have just do this one, just save this one, just go to the this waveform window, relaunch this one. Okay, just click on this waveform window. See here. So here, when A, B, and the scene, these three inputs are off. In place of this sum and in place of this C out, you are going to get the off itself, right? The LED won't blink here. So, and in the next one, I have given the other conditions as well, right? If A is off and B is on and C is off. In place of this sum, the LED is in place of the LED, in place of the sum LED, it's going to blink, and the C out LED it won't blink. Okay, so in the next one, A I have given the off, and the B C I have given the on condition, right? Whereas in the sum, the LED won't blink. In the C out, the LED is going to blink here. So in the last condition which I have given, A B it will going to be on, and C in it going to be the off, right? So in this condition, the C out will be is going to be the LED is going to be the on, and in the sum the LEDs won't blink here. So this is how we are going to write the code in the Xilinx, and this is how we are going to write the code in the Xilinx. So and we have to verify, like after writing the code also, you will be like just now we have saw, right, until like in the last minute, like in the waveform window, we come to know that there we got the there we have done the mistake, right. So you have to, like, after writing the test bench only, like showing the, like seeing the waveform window only, you come to know that the circuit which you have designed, whether it may be the full adder, half adder, or the multiplexer, demultiplexer, the thing will be like it going to perform in a particular way. The full adder means it going to add, right? Like for subtraction, what are the circuit you have designed, it will perform that certain operation like the addition or the multiplication in the waveform. Like here only we come to know that the circuit which you have done, it will be the successful or the not. Okay. So in this way, we are going to write the code and we have to dump the code. Like I have mentioned here. See, first thing I'm just revising those all things. Synthesize we have to do, and this implement design also we have to do. And here we will be having the generate program, right? So we are going to dump the code in the two ways. It is nothing but the JTAG. By using the JTAG, we can do. Uh, by using the USB also, you can do dump the code in the FPGA. So the companies, the VLSI companies which we have, there's nothing but the Intel or the Microchip or the AMD or the Xilinx. These are the few VLSI companies which we have, and more also we have. These are the few which I'm saying: Intel or the Microchip, Analog Devices, the Xilinx, the Skywatch, or the AMD. And when come to the role of the VLSI in the future, like the future of the VLSI technology looks promising, and it's a booming technology also we can say, with new innovations such as in the artificial intelligence or in the IoT, like the driving the demand for more powerful and energy efficient chips, and in the development of the 5G technology is also expected to drive the demand for the VLSI technology in the upcoming years. In the like they are also we are using this one, right? So VLSI is nothing but it is a booming technology we can say here. So once again, thank you so much for the connecting this webinar. Kuppam Engineering College webinar on the FPGA based systems, Department of the EC. Thank you so much for conducting this webinar. For the conducted with the convener is the Dr. G.N. Kodanda Ramaiah sir, and the coordinators Dr. P. Jayakumar Reddy sir and the Dr. K. Rasadurai sir. Thank you so much for conducting this FPGA based systems. So, if you have any, if you need any project or if you need any internships or if you want to conduct any more webinars from the Pantech, you can contact the information, like you can contact to this number. So, if you have any queries, just let me know in the comment section. I'm going to give the reply for you. So, if you have need the help from the Pantech, like in the mini project or the major project or the internships, or else you need the any workshops or the webinars, you can just contact to this number which I have given on the screen. So thank you so much for Kuppam Engineering College Department of the EC to conduct this webinar on FPGA based systems. So if you have any queries, just let me know in the comment section. Thank you so much, Neelakantappa. So if you have any queries, just let me know in the comment section. Thank you so much, Rameshwar. Attendance link will be shared in the comment section. Just you can check it out. Thank you so much, sir. So if you have any query, just let me know in the comment section. So once again, thank you so much for the Kuppam Engineering College for connecting the FPGA based system. Thank you for the convener and the coordinators. Thank you so much.